All right. So today we are going to take the model that we built yesterday, and we'll do a bit of review of kind of everything up to this point. We're going to do the full data pre-processing that we learned about previously, and then we are going to use it to actually train the model. Um, and we'll be talking about data sets, the training loop. So it's not just one row of water potability data, but all of the water potability data that we're using. And we'll dive into how the training model works, and our model will finally learn. And we'll talk about how it does that with something called the loss function, optimizers, and backpropagation without really getting into the math. And we'll see our full training loop. And if we have time, we will also test out our model. And we'll be doing this with our water potability data and the model we were playing with yesterday. Do folks have any questions about the plan for today's lesson? Awesome. And just to orient everyone, I've got my Jupyter notebook over here. I've got the water potability data here. I've just made a virtual environment in the same directory. And I'm going to close out the side editor so we get a little more screen real estate. So let's take a quick review of where we started and where we ended up here. So when we started this journey, we talked about how what learning models do, and specifically a binary classification model, is we feed it some sort of input, such as the picture of a cloud. That input has to be broken up into a whole bunch of different data points. For an image of a cloud, it would be pixels. For our water potability data, it's all those different data points. We've seen how we use tensors to hold and manage those data points and to build our model. We've seen how we have to do some pre-processing of this data. We have to fit the data within, we have to do some normalization and standardization so that our model can efficiently learn with the data and the outliers don't skew anything or extreme ranges don't impact the training of the model. And we have to get rid of null values. Um, we've seen how once we've done this, we then have to break up and organize our data even further, where we have features, which is the inputs to our model, the different pixels of the cloud, or for water potability, pH, and hardness. And then we have labels or the target, which is telling us it's the answers to the quiz, right? That this is a cloud, or the water is or isn't potable. And we have to organize our data because just like if we're taking a class and we're learning new material and studying for a test, I need some practice quizzes and some questions for practice. But then for the test itself, I need some different questions. Because if I used the practice questions on the test, we'd teach to the test, we'd overfit the model, and it wouldn't be very good. And yesterday, we really kind of dug into this funnel to see what's going on and how this binary classification model works, right? And that's what we've really kind of been doing over the last 2 days, where we have these different layers. And I can't quite get it all. Let's see if we can get the whole thing in one screen. We can almost get the whole thing in one screen. We have our input, um, and so far, we've only dealt with one row of data at a time, right? One tensor. Our input layer has a neuron for each feature in our input, such as pH and hardness and what is it like trichloromethanes. We've seen how tensors are used to build weights and biases based off of random numbers, and those input features are then passed on to other neurons, and how to build different linear layers that do number crunching with weights and biases, doing some tensor multiplication, and that finally get to an activation function, um, for which we're using a math function called a sigmoid, which squishes our data into a value between 0 and 1. So we get an output between 0 and 1. And that's our model's prediction whether we can drink this water or not. And we saw yesterday how if we can make a somewhat more complex model for water potability with additional layers, and I'm not going to draw all the neurons and stuff like that, because it would just be a lot of circles here, right? I would need 18 of these, but we have 9 inputs. We expand it to 18 so that our model can do more number crunching, essentially. And then we need to gradually shrink it down by numbers that are powers of 2 or multiples of 2 to get to our sigmoid. And so this is what we built and played with yesterday. Today we're going to build this, but we're also going to train the model by actually finally doing the learning. And let's make this a really nice big arrow. With backpropagation, and something called a loss function, which is going to be, in essence, the difference between the prediction and the real answer, right? If the question on the quiz was, what's 3 plus 3, it really actually the better analogy is, did I get 2 out of 10 questions right? Did I get 8 out of 10 questions right on the quiz? Our loss function does some math to essentially calculate that value to give us a score. And back propagation is actually going to work back through all the different weights and biases in each layer. And I'll make a couple of these. Let's just grab 3 of these guys, just so we have something to see. And just to remind us that these all are connected to each other. And I'm not going to draw all the arrows because that would take a while. I'll just sort of draw one per layer just to help us visualize, if that makes sense. Does that work for everyone?
Yes, indeed.
Cool. Awesome. Because indeed, what we're going to see is that what backpropagation is doing is, and I have these things overlapping, so we're just going to have to live with that one. What backpropagation is doing is it's moving using this loss function to work back to each weight and tweak it to try and make it better. Well, that's really optimization as well. But once we know how wrong we were, we go backwards to figure out where we went wrong. And then we tweak the weights and biases to try to get us a number that's closer to the answer. And we do this essentially a couple thousand times. So this is what we're going to kind of dig into and cover over the course of today and actually build and do. And this is what we really mean by training, where we're running our model and now we're doing this sort of loss function, backpropagation, optimization to tweak weights and biases to make the prediction better and better and better using all this data that we have and that we've organized and collated and classified.
I'm not sure if I missed it or, however, but how do we get the target of the real answer that we're looking for?
Yeah,
Or I guess like how do we set that? Is that something that we're going over today as well?
great question. And good news is this one is really straightforward. I think it's just easy to get lost in the sauce. We already have it with the water potability data. That potability number, that is our target, right? Because that tells us
Right,
if the water is drinkable or not.
right. But didn't we also take off the water potability because we didn't want it included in our data?
Yes,
Well, the label, right?
and that you're correct. Yeah, and we called it, and we're also calling it a label or a target. And indeed, today we're going to add it back in. Let's see if I can get the compact view here. This is, there we go. Today we're going to add it back in the code as we build it because we still have it there, right? We just didn't feed it into the model when we ran yesterday. And that's one of the additional things we're going to learn about and do today is to give our model that potability information, that label or that target.
As that target. Cool.
Yeah, great question. What other questions do folks have?
I just wanted to add that speaking while we're on the subject of targets, like it's industry standard that your target will always be that last column in
Yeah,
the data.
that's an excellent point, James. Thank you. And actually, I didn't know that, but that makes a lot of sense.
So in that case, we want all these ones that we can see to be a potability of 0.
Well, yes, that's correct. We want to, when we're done training our model for for each of these rows, we want it to spit out a number as close as it can be to whatever this potability value is. And again, think of a metaphor sort of like um guess a number between 1 and 20 or 1 and let's say like a number between 1 and 5,000 and I say if you're hot or cold, right? And we kind of get closer each time and refine it. And that's not the actual math. The actual math kind of uses more randomness and statistics, but it's that same principle. Um, what other questions do folks have? That's a great question as well. What else is on people's minds?
And just correct me if I'm wrong, Adam, the in that potability, the zero, is there it should be a one in there somewhere, maybe two, right? So the
Oh
zero would
yeah.
be like for no and one would be yes
Yeah,
or
if we
vice
scroll
versa.
down, I wonder if it's sorted. Yeah, there's just a lot of data points. I'm actually not sure if this potability value has decimal values or if our training data just has zeros and ones. It might just be 0 and 1. But yeah,
Yeah,
1
I,
means it's drinkable, 0 means it's not. Our model is going to spit out a value between 0 and 1, and that's its prediction as to how drinkable this water is. Yeah, great point, because we were looking at all zeros there. All right, I'm gonna kind of leave this up here just to refer back to, but I am gonna kind of sideline it for now. Does this work okay for everyone in terms of screen real estate?
Yes.
Awesome. And in fact, what I'll do for now is I'll just kind of have this up on the side because this is what we're going to kind of build out and work through. I'll just leave it there. Yeah, I'll just kind of scroll and give us some white space. All right, let's start writing some code. And we're going to start off with some things we already did. The first thing we're going to do is build the model. And this is what we went over yesterday. And folks had a great question that I wasn't quite sure about yesterday. Why make a binary model class? Right? Why do that instead of
so that you can use it as an object in some other feature?
Yeah, that's a great point. We can use it as an object in some other feature.
I mean, I was thinking something more along the lines of like, if you need an answer that's either yes or no and not an in between, like, is the water drinkable? Is this air breathable or something like that?
So you're on the right track. It's not necessarily that we need something with more than yes or no. And this is, I honestly wasn't sure about this yesterday, so this was after a little digging. But the short answer is it gives us a whole lot more flexibility. We're not going to see it really in this module, but we might want to have more complex interactions between layers. Maybe there's some sort of branching paths or more complex interactions happening. We might want to reuse layers depending on how complex our model that we're building is. Skipping certain parts of connections between layers. And all this is more complex and not stuff we're going to do just to kind of paint the picture. Chase, like you were saying, if we have like multiple inputs or outputs, and then we might have custom operations we are doing between layers. Maybe we've built our own activation function that's not, part of the PyTorch standard library. So all this is more advanced, but just to kind of touch on this from yesterday, these would be some of the advantages of using a class. And both for learning purposes and just to have a standard approach, I am going to build a class today, and that's what we're going to do in just 1 minute. So yeah, thank you for asking about that yesterday, folks, because that was a good question, and I didn't have an answer to that one at the time. Let's just go ahead and import everything we're going to need now. I know we're going to need PyTorch. I know at some point we're going to need scikit-learn, and in fact, I think I need to install scikit-learn in this virtual environment, which I believe is now done. So I'm just going to do all my imports right now to get them out of the way. We'll eventually need to split up our training data. We might as well do all our torch imports in one spot.
I was wondering as well, if we import, like how we do from Torch import NN as NN, if we don't assign it as NN, could we still use it as NN?
Yeah, I
Because that's
honestly
the name
don't
of it.
think, I think you're correct. I don't think we need this. Um, because I was playing around with that the other day and I was wondering that as well. I am sort of following the curriculum, but I don't think that's an issue. Um,
I just didn't know if that was just to kind of show us we can save it as a different variable or if it was like, like a standardized type of thing that people do.
it's not a standardized thing as far as I know. Maybe there's a gotcha. There's a name conflict I don't know about that we'll see an error. So if we do see a weird error at some point, we'll know to come back. But honestly, I think this is safe. It is nice to see that you can alias stuff because if something has a really long name, that can make your life a little easier. But you're correct. I don't think it's necessary. Like right here, aliasing pandas to PD is nice because it just gives us less to type. Um, I think, in fact, I already imported Torch and tested the version, but all that should be good to go. So we've just got all our imports up here. And I think I'll just have that be its own code cell. And in fact, I'll just go ahead and run it. And while that's doing its thing, I'll make another code block below and we can start building our model. And we're going to build the same model class like we did yesterday. And hopefully that command will finish running and succeed as I build this model. So we're going to make a binary model that's going to import from NN module. We're going to make our init function. We need to call the parent constructor, right? If binary model inherits from module. Our example code does it this way. I did a little digging because there was a good question about this yesterday and I didn't have the answer. I think this is a holdover from Python 2 and we don't need to worry about it. You only need to worry about it if we're inheriting from, say, multiple classes and we need to tell Python which parent to call the dunder init method on, but I don't think that's going to be an issue for us. If we see a weird error, I will eat my words, but I'm pretty sure we can just do this just fine. I don't think I need self here. Can someone just confirm for me that I'm not losing my mind and that's correct, that this looks right?
You need
I think it
self.
looks good.
You need self, I think.
I do need self, thank you.
Oh,
Or we don't need self.
For mine, I also passed in the name of the class and then self.
Yeah. So the name of the class, and that's what I was showing you guys yesterday. Um, I don't think we need that. I think that that's a holdover from Python 2. Um, pretty sure this is right. And in fact, I'll just ask the internet quickly to confirm. Yep, and we probably don't need to pass self. Oh, the other thing to mention here that's actually really good to know. The nice thing about writing a custom class is also, and this really belongs at the top, debugging and logging. Because we can add print statements and all sorts of stuff, which is a big deal. So I want to build the
You do
same
need
layers
self.
that we had
If
yesterday.
if you're
Oh,
going to
yes.
use
Another question?
attributes, if you're going to use attributes under there, you're going to need self.
Say that again, James.
You do need self.
Okay. And you know what? Let's not even, we might as well just not rock the boat if we're doing it this way. Um, so to kind of hop over to our diagram of the model we built yesterday, where we have our input layer, our three hidden layers, and our sigmoid. I'd just love a little help from the class in building the rest of this model. So now that I've called the parent constructor, what do I need to do next in my dunder init method here to build our binary model for water potability?
So you need to build each layer, each linear layer. So you're
Yep.
gonna do self dot linear. And because you'll just do self dot linear, name it linear one, yeah. Equals nn dot linear, and then how many data points you're expecting to put in, and how many you want to, I guess, put out to the next layer. So we want to, yeah, 918. So then we'll do the next one, which will be self dot linear. 2 equals nn dot linear, and then we'll do 18 because that's how many it's expecting to get in, and we'll cut it to 9.
Sounds good.
Or
I like it.
uh, cut it to 12 is what we did with the class.
Yeah. We can do either, whatever you prefer.
Yeah, we'll just do 12 to keep it the same.
Yeah, it's a good call.
And then same thing, self dot linear. We actually need to go up one line and do
Yep.
self dot linear too.
Thank
Yep,
you.
and then 3, and then dot linear, and then we'll do 12, and we'll cut that to 6. And it looks like you have a capital I inside of linear right there. Cool. Yep, self dot linear 3
Let's
or
see.
self dot linear 4, excuse me.
Oh yeah. Yep. And then
Um,
linear, and then we're going from 6 to
6 to 1,
yep.
and
Yeah, take us home, Jack. This is awesome. Thank you.
then self dot sigmoid, and we'll do nn dot sigmoid, and then yeah, no arguments inside of there.
Awesome. Um, and maybe Jack, thank you for walking me through that, and that was awesome. And can someone else help me out with the next step? Now that I have my Dunder and Knit set up, what's the other thing I have to add to this binary model class? How about Kenny? And you can phone a friend if you're not sure.
Uh,
Or
we do the you do
yeah,
the def
go for it.
forward method, right?
Yep, we need a forward method. Um, and what does the forward method do, Chase?
It just from what I understood, it just passes forward the values that's being outputted, I think.
Yep. It basically, if we don't write this forward method, then our model will never actually apply any of the linear layers that we've created, right? And it won't feed the data in. It won't feed it to the next one. It won't feed it to the next one. The same way we did this manually yesterday, we need to tell PyTorch in this forward method to basically, execute each layer and pass the data on. And then anyone want to take a crack at explaining why our forward method is going to return the output of the sigmoid function? And Tim, what are your thoughts?
I have no idea.
No worries, man. I appreciate you saying that. And honestly, that's what this is all about. Who do you want to phone and put on the
Chase
spot?
Chase seems to know what he's talking about.
All right, Chase, go for it, sir. And you can
What
phone
was the
Kenzie
question
if you
again?
want.
Sorry.
Why does our forward method return the output of the sigmoid function?
Because that's the way it works. Honestly, I'm not sure. Just because the sigmoid takes in the last point from the last layer. But other than that, I don't really know the answer.
Yeah, I think that's a good shot. And Kenny, I see your hand up as well, so go for it, please.
I did a little bit of research on this, and I believe that sigmoid is a function that can take in multiple inputs and returns a value either between 1 and 0, which is what we're looking for.
Yeah, yeah, you hit the nail on the head, man. We did not build our model this way. I do think we could have this be three, and sigmoid would take in inputs from all three of those neurons, just like you're saying. And then, like you're saying, sigmoid squeezes that data, does some math to it, and gives us a value between 0 and 1. And that's the activation layer's job. You can actually have multiple activation layers, but the job of our final activation layer is to give us our prediction value, right? So the reason we return the output of that, like you were saying, Kenny, is because that's the prediction of the model for the data that we feed into it. Does that make sense to folks? Cool. Yeah. And again, just imagine like PyTorch is going to call forward every time we feed data into the model. And then this PyTorch module class does the work of, um, well, actually, we do the work right here of we take the output of this, we stick it in here, we stick it in there, we stick it in there, right? And we're just feeding the output from each layer on into the next, and then we return it. And there's more complex things we could do here, like we were saying, but this is sort of the straightforward approach and what we're going to focus on today. And now I'm going to make an instance of our binary model class. And just for fun, and to make sure that I don't have any typos, because I love running code and getting output, let's just print that out. And in fact, that's kind of cool. PyTorch must have a nice dunder string method somewhere in it, and in that nn.module class, and we get a nice printout of the different layers of our model. Do folks have any questions about sort of this step and the model that we just built? Okay, awesome. So our next step here is now we have to do our data pre-processing. And I think what I want to do is get a little help from you guys and just sort of like pseudo coding this out. Just help remind me what the different steps are. And in the interest of time, I'll build it out. Though if people want to, I would love for folks to be the driver. I also do have the curriculum from that day pulled up so I don't get lost in the sauce like we did yesterday. So once I have my water potability data, what do I have to do with it before I can feed it into the model? What are some of the things that have to happen?
You need
We
to
have
get
to,
rid of like the null values.
Yeah, we have to get rid of nulls. Um, I think someone else was going to throw something in there as well.
I was gonna say, I mean, we have to import it as well, don't we?
We absolutely do have to import it. Um, and what library do I use to import and pre-process the data again?
Uh, CSV, but is it CSV and pandas?
Is pandas.
Okay.
Yeah. Yeah, indeed pandas has a CSV method and it might use some Python built-in CSV stuff under the hood, but we're going to import our CSV data with pandas. And let me just call on someone. Rachel, what else do we have to do in our data pre-processing?
Split into features and targets, and then split again into testing and training.
Yeah, totally. Did you say break into features and targets? I just missed the first part of what you said.
Yes, yeah.
And remind me again, what's a feature? What's a target?
Your features are like any variable that will help determine your target, and then your target in this case will be the potability.
Targets are labels, right?
Yup.
Okay.
Yeah. Yeah. Great point. Yeah. Well, I kind of go interchangeably. And can someone,
I'm
Stephanie,
sorry, I have a
oh yeah,
question.
what's up?
Um, are they not all labels? Like, are features not labels as well?
Features are not labels. That's correct.
Okay,
Uh,
so I guess what is a label?
uh, a label is our water potability. Um, Rachel, you might know better than I do. Is there like a meaningful difference between target or label, or are they both just kind of different ways of saying the same thing?
Yeah, different ways of saying the same thing. For features, you could also say variables. In this case, like for the binary classification, the label would be 0 or 1.
Think
Got
of
it.
labels as the answers, right?
Say that again.
Labels are the answers, and
Correct.
features are what we want to give us answers, right? To add up to labels.
Yep. Exactly. Features or labels are the answers. Are sorry, so many terms. Targets or labels are the answers,
Yes.
and features are the data points we use to calculate an answer.
Yes.
Yeah. And
Got it.
Rachel, that's a great point that the label here is also, we know it's going to be 0 and 1, that we've got our values. And can someone remind me, why do I need to break my data into a training group and an evaluation group?
I'm assuming part of it is that in the process of backwards propagation, you need to know what you're correcting. You, the model gives you an answer, and depending how close it is to the actual answer, you have it go back, fix certain parameters, go forward, see if it can get the answer, and go backwards multiple iterations.
Uh,
Another reason is if you train your model on all the data, you'll like put bias and overfitting into your model.
yeah, that's a great point, Rachel. And Kenny, I think you're in the ballpark as well. And just to touch on those points, Rachel, like you're saying, if we don't have any evaluation data, we teach to the test. And I think this is a good metaphor here where, again, if the actual quiz is the same as the practice quiz, we can just memorize stuff, but we don't actually learn anything. And Kenny, like you were saying, the training data, including features and targets, is used to refine the model, right? For looking at how poorly we did and back propagation. Um, and Rachel, am I right in thinking that sort of like after each time we, feed our data, like one row of data into the model, does evaluation get used constantly in the training loop or at the end of all the training? I'm actually not sure about that one.
What was your question again?
Does the evaluation data get used for at the end of all the training or like at the end of each individual loop, if that makes sense?
So for the evaluation data, like ultimately with the model you create from the training data, you'll create predictions and then you'll compare your predictions, in this case of the potability, to the um, evaluation data. And then, so you would use the feature evaluation data set to create predictions, and then you would compare those predictions of the target to the evaluation target data. And then from that, you can get an accuracy score.
And that happens essentially right after each run of training to see how well it's doing and if we should be tweaking different parts of the model. If I am I in the ballpark there?
So you use within like each run of your model when you start training it, you'll compute the outputs or the Y predictions, the
Mhm.
target predictions, and then you'll use the Y predictions to like within your loss function, and then from there, that's how you train the model. But then once the model's trained, then you'll feed it the evaluation data.
Got it. Thank you. Yeah, and folks, we'll actually build this and walk through this a bit later. And Rachel, thank you for your help on this. As I said, like I'm learning a lot of this as well. Um, and again, I think the right analogy here is the training data is like to study for the test and all the practice quizzes during class and stuff. And then at the end, we have the big test, and the evaluation data is what we use to see how well we did on the test. Right? Because once we train a model, we might need to go back and tweak stuff if the model isn't doing so great. Maybe I need to change the number of linear layers. Maybe I need to change the number of neurons in each layer or use a different activation function or something like that. And hopefully I'm in the ballpark on that one. So training and evaluation data is a big deal. And just to recap data processing, we're going to import it with pandas. We're going to get rid of nulls. There's one more thing I think we need to do here that we didn't touch on with pre-processing.
Is it
The
standardizing the
fit
data?
transform.
Yeah, transform. And Noah, I think you were going to say something as well.
Standardizing?
Yeah. And I think that's everything. If I am missing a step, let me know, but I think we have, oh, and then at some point we need to turn it into tensors, which might in fact happen before we break it into features and targets. I'm not sure. And remember that our training data does include labels as part of the training process. It looks at the correct answers just like we would for a practice test. Let's see. It's 10 till. This is actually, I think, a good stopping point because the next step, I think, is after the break, now that we've walked through this, and this is the important part, right? Like if you go into a job interview and you can confidently talk about this, um, the nitty-gritty details of getting the Python code correct are great and super valuable, but a lot of the times just being solid on the concepts gets you more than halfway there. Um, and that's why I kind of love to have us do some of this pseudo coding in essence. So let's take a 10-minute break. When we reconvene, I'll go ahead and implement what we pseudo coded out, and we'll have our data cleaned up, and then we can start training our model. Sound good? All right, awesome. Great job, folks. Thank you. Great job on the Q&A. I know I'm kind of putting some folks on the spot, so I appreciate it, and I think it's helpful. Have a good break, and I'll see everyone in 10 minutes. All right, so we've kind of reviewed what our learning model looks like that we've built. And in fact, we've gone ahead and we've built it. And then we did some good pseudo coding of the steps we need to process our CSV data, all this water potability data that's in this CSV file. And in fact, why don't we just, as a friendly reminder of what the actual data itself looks like. It's just this first row here with headers, and then row after row of data with that last value being, a 0 or 1 indicating the water potability. And this is what we're going to manipulate with pandas and be feeding into our model and training our model against. To pre-process this data, we got to import it with pandas. We're going to get rid of nulls. We're going to use fit and transform to scale the data. We do have to break it up into features and targets. We don't want to fit transform the targets or the labels, the potability value, and we need to break all of our data, features and targets, into training and evaluation data sets and turn it into tensors. So let's go ahead and start doing some of this. And let me just switch this over to Python. And I'm just gonna dive on in here. I'll use df for data file. And PD, I believe, is pandas. And we're gonna read from our CSV file to get our water potability data. And let's just print out df, what is it, iloc. I just want to print something out to make sure I haven't done anything silly. And indeed, I've got data here, which is all I needed to check. So now let's go ahead and fill in null values with the average or the mean value. And we're doing this for our features. And truth be told, all the labels, all the potability values in the CSV, I think are 0 and 1. So I think we can just fill in the whole thing and not have to worry about it. So we're going to tell pandas we're going to use the mean. We're going to tell pandas, I don't want a new data frame with all my data. I want you to modify the one we already have. And let's just go ahead and make sure that we don't have any null values in our data. And we can see that now, indeed, we have 0 null values anywhere. So that's a good step. Let's go ahead and do some more data pre-processing. And let's go ahead and start building up our features and labels. And this was where I got lost in the sauce yesterday. And Chase, thank you and everyone else for kind of helping me through this one. We need to tell pandas the name of the column, right? Our CSV value that we're going to drop. And the axis, I believe, maybe has to do with like how nested the data is. I honestly would have to double check exactly what this axis property is doing here. But
The axis will just be like if you want the rows or the columns.
Say that again.
The axis can be 0 or 1 for if you're trying to drop the row or the column.
Okay. That makes sense. That makes sense. Thank you. And is that sort of related to dimensionality?
I'm not sure.
I'm not entirely sure either, but that kind of makes sense that we can specify if we want to get rid of a row or get rid of a column. And we're essentially saying get rid of the whole potability column. And let's go ahead and grab our labels as well. That
I
drop,
do have a question.
yeah.
Oh, never mind. You might be about to answer it right now.
Oh, well, let's go
It was
ahead.
basically just about the eye lock though. Like, um, doing the features that drop, is that doing the same thing as like the eye lock with the -1?
I want to say iLock, that would give me a slice of rows, but wouldn't get rid of potability from those rows. Does that make sense?
Yeah, I just, I mean, because I kind of, as I was doing this yesterday, I have it with the iLock, and it did get rid of potability, but I'm wondering if it like got rid of it altogether through my data, and I won't be able to reference it later if like it's creating that sort of issue. It's iLock, and then it's a colon, comma, space, colon -1,
Got it. iLock.
colon, uh, comma, space, colon -1.
Oh, this may actually icy or past like this in the side of the
Yeah,
square brackets.
correct.
This may be a more advanced use of iLock that I'm not familiar with. Let's see what happens here if this gets rid of turbidity or not. And indeed, it does. You're right. Um, I don't know off the top of my head if one way works better than the other. I think if nothing complains, then you're good to go with either one. Um, I think the only reason to maybe go for drop is for readability and intent with other people looking at the code. But to be honest, I'm not sure. And that's cool. I didn't know about this. It looks like what we can do here is like I could maybe specify I want one row, but here we're saying get rid of the last
The
column
last one. Yeah.
on that row, which I didn't know I actually didn't realize we could do that with iLock. That's awesome. And that would actually be a good chat GPT question. Like, is there a difference between these two things? Normally I would just look that up on the spot in the interest of time. I don't want to open that door, but that if someone can and share the answer, that would actually be really good to know. And drop does indeed return a new data frame. So our original data frame with our potability data, our water data, still has both features and labels. Um, so we can grab the labels and let's just print that as well as a sanity check. And indeed, I've got my features and my labels. And now let's do some standardization and normalization. And we'll feed into it our features. And let's just print this out real quick, just to make sure we're seeing something good. And this looks right. I'm seeing this E, this sort of like raised to this -16 power. That tells me that indeed we've got standardization applied. Let's break up our data into training and evaluation groups. And we're going to have training features and evaluation or testing features. We're going to have training labels and evaluation or testing labels. And we're going to use Panda's train scikit-learn's train test split function to do this and we'll pass in our standardized features, our labels, and we'll tell it that we only want 20% of all of the data to be our test data. And this returns a tuple, remember. And this is just some Python syntactic sugar to assign each of the elements in that tuple to its own variable so we can work with them. And let's just go ahead and print some of these out real quick just to make sure that everything looks more or less right. So I'll print out a feature from one and a label from the other. And I'm seeing stuff, which is what I want to see. And so now let's turn our data into tensors. And we need to convert to floating point 32-bit data types. The training, the feature data might already be there, but it certainly isn't going to hurt to do this casting. And I'm always a fan of being explicit. And I do need an equal sign over here. So let's go ahead and fix that. And let's also just do the same thing for our testing features. And I'm doing the features together because we do it the exact same way. Then with the labels, we have to do a little bit more work to add an extra layer to turn this nicely into a tensor. Because right now, if I just do training L, and I do it the same way that I did with the feature data, we will get an error. And let's watch that error happen. Because I think this is a common gotcha that's good to see, and then we will fix it. So the error here is could not determine the shape of object type series. Basically, that's telling us that this data is not in some list type format that we need. If we do dot values, it'll turn it from pandas data frame into a NumPy something that is essentially a nested array. And that does work, but I do think we need to add one more thing to change the shape of this tensor. I think we want an extra layer to our tensor, if I have this right. And now we have each label as its own row, right? We added another dimension, I believe, to the we restructured the tensor. And I think this is the way we need it when we feed it into our model. And let me go ahead and do the same thing here for our testing labels. And I'm just going to change that value as well. And we'll just print that out just to make sure it's looking good. And now we should have our data processed and ready to go. Now we are kind of coming into a new area, which is data loaders. So data loaders do a couple things for us. Unlike yesterday, where we were really only feeding in one row of our data, we're going to feed in all the data to our model and have it do a whole bunch of runs, right? And we'll get a whole bunch of predictions. And data loaders are going to help with that for big batches of data. And as a part of that, improving specifically the memory efficiency of loading this data and working with this data and manipulating it. And then lastly, and very importantly, helps our code refer back to, I believe it's the training labels that go along with our training features. Right? And again, if we have a practice quiz, we need to know both the questions and the answers as part of the learning process. And data loaders can help with that as well. And that's a big part of it, is to help provide us those labels. And the data loaders are going to kind of put our data into it's sort of a stack data structure, and we haven't talked a ton about stacks, but it's pretty darn similar to a list, and it's going to look something like this. And as with everything, it's all boxes within boxes within boxes. And we'll have our data organized into groups or batches, and we'll have, some labels. And then we'll have our features. And we'll have a whole bunch of these. And TL Draw just did not want to give me that label for some reason. And this is what our data loader is going to help with. And in fact, the PyTorch class is indeed called data loader. And specifically what it's going to build for us is a tensor data set. And that's what we're looking at here. Right? So it's going to, again, just help organize our data for training. And let's kind of bring this over here just so we have it to look at. And let me go ahead and write this code, because I think seeing the code will help illustrate the concept, and then we can pause and check in for questions. So let me go ahead and write some Python. I need to do a little more importing from PyTorch. In their utilities module, they have a data module. And from there, we're going to import a data loader class. And there's a nice description here as well. Data loader combines a data set and a sampler. It provides an iteratable over the given data set. Right? So this is what's going to enable PyTorch to go, as we train our model, from one group of data to the next. Right? And that's kind of a big part of what we're adding in today that we didn't have yesterday. So let's go ahead and import that. we also need to import tensor dataset, which, as it says here, wraps our tensors. So again, it's sort of like layers upon layers of stuff. But at the end of the day, it's all these sort of like matrices, these nested rows, these tensors. And we're going to make a data set for training. And we're going to feed it, not surprisingly, our training features and training labels. And let's just output this and see what this looks like. Nothing super interesting at the moment. We see it's an instance of a class. If we want to play around here, we can kind of see what's inside it. It's got a whole bunch of tensors inside it. Let's see what else it has. Most of these are anything with a double underscore is a method that we're not really meant to interact with directly most of the time. With Dunder and it sort of being the exception. So it's more built-in Python stuff. So we can, in essence, ignore these. And we see that tensors is sort of the main attribute of this class. And let's go ahead and make our testing data set as well. And actually, now that I've made the data sets, I need to put these into some data loaders. So let me go ahead and do that. And then I think that'll be a good time for questions. And I'll talk about in just a minute what batch size is and what shuffle is. And I believe those values should be correct now. So before I dive into batch size and shuffle, I just want to check in and see what questions folks have and what things people are curious about. How are we feeling? On a scale of 0 to 1.
And I'll be honest, I got a little lost in the sauce a little bit.
Yeah, I agree.
Got it. Got it. This is, I think, a good spot to recap. Are we feeling pretty good about all the data pre-processing that we did up here?
I think honestly that was really where. So why didn't we do dot view on F?
Yeah, great question. Let's take a quick look at up here. Let's look at our training features, and then let's look at our training labels. And this is before we've turned them into tensors. And let's get rid of the labels so we can see this one at a time. So our training features, in essence, we have some nested lists here, right? Let me grab the zoom annotator because that highlighter I know is a bit of a pain. If you guys look at sort of the double brackets, that clues us in that we have a bunch of nested lists, which looks an awful lot like a tensor, right? Where we're basically dealing with a bunch of nested lists in a matrix. If I print out, instead of the features, the labels, and the features, there's 9 different things here, right? It's like pH, hardness. I'm making up my terms, but you guys understand what I mean here. Something else, right? There's 9 things. If we just have a simple list representing each row of our CSV data, right? There's not 9 things in there. For the training data, it's just potability. It's just the one thing. And if I print out our labels with our potability information, notice how we don't have the nested list, right? Frankly, I'm not sure why we have this other stuff printed out here. It honestly might be a different print statement altogether, or it could be a row number or something that's added. But the point being is we're not looking at a nested list. For our features, we have two layers of our list to kind of go back to this dimension term from tensors. For our labels, we have one. And that's what causes the problem with trying to turn the labels into a tensor without using view. That basically adds that second layer. So we have like the shape of the nested lists we want to build a tensor. Does that help break it down a bit?
Yes.
Yeah, that's a great question. And I'm probably getting a couple of the details wrong, but the big picture of this should be correct. So that's the big difference here. And the term I like is the shape of the data. And the more you guys think about the shape of the data, the easier life becomes. And the shape of our label data is different than the shape of our training data.
Yeah, that helps.
Yeah, great question. And this is a big concept. There's some old programmer saying, like, show me your flow charts and I will be confused. Show me your like data tables and I will be enlightened. And it's from the 70s or something by some famous programmer guy. And the essence of it is the logic is actually less important than the data. Um, which I do love to talk about like a broken record, and that's a topic for another day. Um, what else are people curious about with these steps here for pre-processing that might be good to touch on? Whether it's big picture or something about an individual line of code where you're curious about what exactly is going on under the hood. And let me actually check our Zoom chat because I apologize. I need to catch up on the Zoom chat and Zulu questions. Okay, so big picture, we've cleaned up, organized our data, and turned it in to tensors, right? We did all this stuff. Now that we did that, all that we're doing over here is using these classes so basically that PyTorch can loop through it, right? Like what we're going to see in a minute is we'll end up building a for loop, and inside that for loop we're going to do, something like this, for just I'm just making this up here just so we have something to look at. For X in my data. Um, Model, I think I just call it like this. Right, there's going to be a lot more stuff happening. But we need a bit more than tensors so that PyTorch can move through all this stuff as we loop and iterate through it and deal with the labels and the features and keep all the dots connected, as we are really taking this whole model that we built and passing the data into it thousands of times and as we'll see in a bit, using the labels, the correct answers to tell PyTorch, you know what? This weight and bias over here made the answer terrible. Make those numbers smaller. Over here, like this weight and bias, it also made the answer terrible. Make these numbers bigger to get closer to the correct answer. And we're going to do this a couple thousand times. And so this data set up here, right, and this data loader up here are really helper classes for us to do this looping through the data and working with it. Does that help a bit in explaining what we're doing over here? And what questions do people have?
I do have a question. I'm just not really sure how to like word it, or if I'm just maybe looking a little bit too broadly at it. But something about like the 80% for testing and the 20% for something else from yesterday.
Mhm.
I guess how do we set that? Like how are we only is that what the batch size is? Is we're only grabbing a certain amount of this data to put towards what we're looking for our sigmoid or
Great question. Batch size is something else that we're going to talk about that we haven't talked about yet. It is kind of hidden. It is this test size number over here, if you all can see where I'm highlighting it, where I don't give it a percent, but I give it a decimal value, right? So 0.2 is 20%. And if I change this, instead of 0.2 to 0.5, then 50% of our data would be for the test group. Yeah, great question. You asked it great, by the way. I think the only bad way to ask a question is the one that's never asked. And indeed, there's a lot going on here, so it's easy to miss this one and have that get lost in the sauce.
so I guess when we back propagate, is
Mhm.
that the 20% that is going back through and saying, hey, you need to fix this weight and this bias? Is that how that works?
Let's talk about that later. And Rachel, you were kind of helping me. I think the short answer is no. When we back propagate, and there is a lot of jargon, when we back propagate, we're using the training labels. And again, think about practice quizzes, right? I've got both the questions and the answers for my practice quiz, and we're using the practice quizzes when we back propagate. And the testing data is for the final exam.
Okay,
Yeah. But if we don't get a good grade on the final exam, we get to take the class again and change our study habits.
gotcha.
Yeah, like we'll add another linear layer and we'll, tweak the number of neurons and I'll, join a study group or what have you. Um, so, big picture, yeah, we're using that evaluation data to improve our model, but it's not part of the training process. And if I'm getting that wrong, someone please let me know. Yeah, great question, Jack. Thank you. What else is on people's minds? What else are folks curious about? And if you are feeling below a 0.5, I would encourage you to just, throw the shot in the dark and share what's on your mind. Because now is the best time to do it.
This may be a little bit dumb, but how are you splitting into four different variables on line 13?
Yeah, that's a great question. Um, so this train test split function actually returns, does it return a list? I thought it returned a tuple. It looks like it returns a list. And so let me just copy this. And can everyone read this code okay, by the way?
Yes.
So the very first thing in the list, shoot, so sorry about that. The Jupyter notebook and my editor shortcuts kind of fight with each other sometimes. And the reason I know which is which in the list is because that's what the PyTorch docs tell us how this function returns this list, right? So this is just how the function works. It's like, if you wrote a function, you get to decide what's in the list, then it's the same thing here. And I think it was like test features, and then we discovered the other day that this was the training labels, and this was the test labels. And if we print out, and in fact, if I would have to change these, and let's go ahead and let's print out the list 3 just for fun and run this. Now I have too much stuff printing out here. There we go. So that's our feature data, right? Our training feature data. That's our testing feature data and so on. And then what we just do here, let's call it destructuring, even if it's not. So instead of having to do this,
Essentially, it's just destructuring under the hood, basically.
yeah, exactly. So it's the term is syntactic sugar, which is programmer speak for 2 ways to do the same thing with a programming language, but one way takes less typing. These 2 things do exactly the same thing. Python's just given us a little shortcut in terms of how we write our code. Does that
No,
help?
I appreciate it. I just
Yeah.
very much suck with destructuring. So when you did that, I didn't understand.
Yeah. Great question. And we don't do as much destructuring in Python. I thought this was a tuple and I was wrong. So it's easy to get mixed up on this stuff. What else is on people's minds? What other questions do folks have? Okay, let's talk about batch size, right? Because we've processed our data and we've chunked it up into these groups using data loader and data set that are really helpers. So let me briefly talk about batch size and shuffle. And then we'll take a break. Sound good? Awesome. So, and I just want to get rid of that. This code isn't going to work, but it will help explain it. For row in training data set, and let me make sure I get the description of batch size correct here. How many samples per batch to load? So this is probably not quite right, but let's just pretend it is. this is in essence the code we're going to write. And so batch size says like how many rows of data is in a batch? Because some of this learning stuff with like optimization functions and batch propagation, it probably doesn't make sense to do it after literally every single row of putting this into our model. Because that's not a lot of data. You know what I mean? Like it's like you want to get a nice little sample size of stuff. Like if I'm doing a little quiz and polling everyone in the class to ask what your favorite food is, if I only ask one person, that's a terrible poll, right? If I ask like 5 people, that's pretty good. If I ask 10 people, that's great, but maybe, I missed someone's favorite food and I want to ask 5 people so I can get the food I missed to make a better quiz for the next group of people. So batch size, I think, is in essence how many rows of data, how many samples. Each row is a sample that we're feeding into our model. We run before we do the learning stuff. And so our training data gets chunked up into batches. And so since everything is boxes within boxes, let me throw in a couple more boxes in the mix. And let me zoom in a bit so this is easier for us to see. And let me give us a little more room to look at it. And what we see in red here is, in essence, our batch size. And you want to use multiples of 2. 32 is the standard batch size. If I make the batch size really big, then you know what? My model runs quicker, but it doesn't learn as well. So 32 is sort of the standard starting number for a batch size. And you want to kind of tend to lower numbers so that we get more iterations. You know what I mean? So that we get more practice tests in before the final exam. Yeah, it's a great question about batch size. And does that help break down a bit what it's doing for us?
Yes, but I guess I also wonder, so like for the water potability, there's like, I don't know, 3,500 different lines. Does it just like take 0 through 32 and then 33 through, 64? Does it just kind of go like that for batch size?
Great question. Um, it does, and it does not. And in fact, I think I have an error in my code, and let's fix this right here. I don't think we want shuffle. So what shuffle does is it addresses exactly what you're asking about. And if we scroll down a bit and read about it in the docs, it reshuffles the data every time. An epoch is like the whole run of all the data when we do all the loops. So with shuffle on, it will shuffle the data before we start, just like with shuffling a deck of cards before you play, because what if the data happens to be in some sort of particular order and that screws up the model? So for training, shuffling is important. For testing, I don't think it's important. I might be wrong there, but I'm relatively sure. So yeah, that's a great question. We definitely want to shuffle our training data. What other questions do folks have? What else are people curious about? 'Cause these are good questions, and this is good stuff to dig into. All right. In that case, let's take a 10-minute break. And then when we come back, I think what we'll do is we will actually write the code to run our model to do the learning. And then once we have that running, we can talk a bit about the learning process itself, because I think it'll help us to write the code and then dig into the concepts. Sound good? Awesome. Thank you very much, everyone. And I'll see you all. You all want to do 10 or 15?
Can we do 15?
Let's do it. Let's take 15, get away from the screen, and then we will train our model. Thank you, everyone, and see you all in a little bit. All right. So today we've done some overall review. We've built a model, a binary classification model. We've pre-processed our data. We've chunked it up into batches so that we can effectively train the model on it, right? If I'm taking the SAT or one of these standardized tests, I need practice quizzes on algebra and maybe on vocabulary words and different subjects, and I just need to organize everything. And that's what we've done here. Now we're actually going to build our training loop. And once it's built and running, we'll walk through what it does. Right? And so we're going to take this pseudocode and we're going to turn it into real code. And our training loop is going to do a couple things. It's going to feed in a whole batch to the model and run it. And a batch is basically 32 rows. After each batch, it's going to calculate how wrong it was and adjust. And this is what's called the loss function, backpropagation, and optimization. And I'll just put these, I think, like this. And it's going to do this for all the batches. There's a term, an epoch, that is all of our batches, all our training data, right? All those thousands of rows, when we have run this model for all of those, that's one epoch. And once we build and run this, we'll talk about how these things happen. Do folks have any questions before we dive in and start writing code? Okay, cool. And I think I'll just kind of leave these off to the side so we can just have something visual to look at. So let's turn this pseudocode into real code. I need to do a little importing from PyTorch. We're going to make our optimizer, and this is what tells the model, hey, you know what? Practice more algebra, or you went too far south. Like, take 3 steps to the north. It tells it how to adjust. And we'll talk about what this is doing later, but it's using an algorithm essentially called Atom, which indeed has the same name as me, but has nothing to do with me. And we'll talk about what these values are later, but we will definitely come back to them. And we're also going to create something called a criterion, which helps us figure out how wrong we were. And let's in fact put this first. And I'll add some notes. I think maybe it's better to say this tells us where we went wrong. And this tells us how to make it better. And again, we'll dig into this once it's written out and running. We're going to have a nested loop. Let's say that we're going to run through the whole data set 2 times, just for 2 epochs, just to start with. In reality, this would be something like 200 or 300. I'm going to run it with low numbers to make sure my computer doesn't freeze up too much. And we're just going to get an index. And our model has a method named train that we can call. And it sets the model, as it says here, in training mode. And let's see, and I do want to make sure I'm not missing a step here. But now we do our nested loop over our training data that we put into our training loader. So now we're going to go through each batch. And we've got our features like pH, hardness, and so on, and the labels if the water is potable or not for each sample or data point. And I forgot something on line 4. Now we have an optimizer. And we're going to reset it for each batch. We need to actually run the model and feed in our data. And we're going to make sure it's all floating point. And now that we have the output, we're going to figure out how badly did we do. And this is what's called a loss function. And let me actually just change this. And in essence, this tells me I got 5 out of 10 questions right on the quiz, on the practice quiz. Or, you know what, you're 50 miles from where you're supposed to be, right? If we're hiking somewhere and I'm going in the wrong direction, the loss function tells me how far away I am from the destination. And we got to give it the model output and we got to give it the correct answers. And now we use our training label data. And we need to put the training label data in the right shape and make sure it's a floating point number. And let me make sure I have my parentheses right. I believe this is now the back propagation step where we figure out where we went wrong, right? Did I go too far north or too far south? Did I struggle with the algebra questions on the practice quiz or the vocabulary questions? If we hop over to our diagram, which got zoomed in crazy big, the back propagation says, you know what? The weights and biases here really screwed stuff up, make them smaller. You know what? The weights and biases here screwed stuff up, make them bigger, right? And so that backpropagation is going to use the loss function to move backwards through each layer and tweak it to try and hit the mark. And the optimizer tells it what to change. Like, all right, I went too far north. Let's take 10 steps, right? Because if I'm trying to get from Chicago to Colorado and I overshoot and I go all the way to California, just saying, hey, go east isn't helpful. Do I go east 1 mile, 1,000 miles, 10,000 miles? How far do I need to go? Right. And so the loss function tells me how far away I am. Backwards propagation tells me where I went wrong. The optimizer tells me how far I need to go to get closer to being right. And so our last step here is indeed to use the optimizer to improve the model just a bit. And finally, we're going to add a print statement for each epoch so we can just see some information. And we'll just print out which epoch we're looking at here. And I have a misspelling on line 8. Just so we don't see 0, we can see epoch 1, epoch 2, and the total number of epochs. We can see how wrong we were. And I think that's a good start. And now it's time to have our moment of truth and run this code. And for the first time, really train a model to learn and get better and see if I have any typos. And not surprisingly, I do. Luckily, this is probably a pretty easy fix. Let's see what I did wrong here.
You just have to take the S off of backward.
Oh, I love it. That's why a second set of eyes is so good. Thank you. That's best kind of problem to have. And this is also going to be an easy fix. Probably this doesn't need an S as well. And now we, in fact, have run through all those thousands of rows of data that we batched up into groups of 32. We ran through all of them twice, right? That's 2 epochs. And the higher this loss number, I believe, the worse we did, because it's telling us how far off the mark we are, how many questions did I get wrong on the practice quiz. And I got a bit better, right? I got like 3% better from 70% to 67%, but not a ton. Let's try running this for 20 epochs. And this is interesting, because if we take a look here, and let me grab our Zoom annotator and highlighter, we definitely see some change, right? If I'm making like a graph, and this is our loss value, then let's just make this nice and big. Right? How wrong we are. And then the x-axis is in effect like each the x-axis is a little tricky to talk about, but it is, let's say, all our model params, weights and biases. And can everyone read these labels okay? I realize they're a bit small. Okay, awesome. And I'm going to draw some hash marks here just to visualize, not to actually represent real quantities. And we'll get the top of the y-axis, and then we can start drawing stuff in. So when I say all our model params, imagine this one data point. Let's put it over here. And we'll say, you know, the higher up, like, this is more wrong. And this is less wrong. I'm actually not sure if the loss function goes below 0 or not. It might just be between 0 and 1. So this data point up there on the left, and I'll make it a little bigger, we're pretty wrong, right? And that's what our y-axis here represents. But this x-axis is a little interesting, because what this is all of those weights and biases in our tensor. You know, it might be, I'm just going to write it out like this, even though it's not how it looks, just so we can have a visualization. And each of these rows will be a layer. And I know that this is wrong because there should be nested lists for the weights. I just don't want to get too lost in the sauce with drawing too much in the diagram. So does that make sense, everyone? This is not exact. This is just like a rough approximation. So this one spot on the x-axis actually represents all the values for our weights and biases in the whole model for all the layers. And so over here, where maybe, you know, we're less wrong, these are different weights and biases. And I'll just throw in some other numbers here just so we have other numbers. And this is, I think this is, I forgot if it's called the loss graph or like the optimization graph, but these data points get filled in every time we go through a whole batch, right? Because with one row, it's not really enough data. But if I feed 32 rows into my model, then I can come up with a data point that says, hey, you know what, Adam, for these weights and biases, this is how we did. And I eventually add more data points to my model every time I run a batch, right? So when we go through a whole epoch, maybe, I don't know how many batches we have. 1, 2, 3, 4, 5. Let's just pretend we have 8 batches in an epoch, just so we have a nice power of 2, because computers love powers of 2. So we've got 1, 2, 3, 4, 5, 6, 7, 8. And let's say that this was our the data from epoch 1, right? And PyTorch keeps track of all this. And we'll talk a bit about how these values get improved, because indeed what the optimizer and the loss function and the backpropagation do is tweak the weights and biases to make them better. We'll talk about how it makes them better in a minute, but they get a little better each time. So for epoch 2, and let's have epoch 2 be in red, we get some data points, and I'm going to put a couple below. I probably should have had the wrongness be on the negative side. let's just say that we want to be right at 0 for our loss function. That, I can go too far north or I can go too far south, just for the sake of argument. So let's say we have some really wrong things, but then we start doing better and we get really close. And now that's batch 5 and batch 6 and batch 7 and batch 8, right? And our graph for epoch 2 maybe looks a bit like that. And, once we do, like, instead of, say, 20 epochs, if I do 200 epochs and I run the learning model, and we'll give it a minute, let's see how our loss function does, telling us how wrong we are. To be honest, it didn't really, I'm not sure if it really got better by the end. I see more 6s than 7s in here. Let's try 1,000. This might take a minute. But I'm curious to see if we end up towards the end with our loss function with this loss getting smaller. I saw 5 creep by. Honestly, I'm not sure if we're going to be able to see like a real improvement in the loss function. And that might tell us I have something I need to change in my model. Maybe I need to get rid of a linear layer. Maybe I need to change the number of neurons in a layer. A lot of, frankly, tweaking the model is trial and error. Now, I do see 6 here and a lot of 6s. And, when we just did it for a couple epochs, like let's just run it for 5. We have a pretty wide range, but we have some bad values in here. So my model may not be very good, but we can see how if we run this a whole lot, we end up with a whole lot of data points.
I do have a question.
Yeah.
Um, we're still going from 9 to 18 data points, right?
Correct, in that first layer.
So is that essentially where that difference is coming in within the epochs, like where that, I guess, multiplication happens at is why the loss number is, changing negatively instead of positively because we're adding more data points?
Say that one more time.
Like, is that loss number, because the way I'm thinking it should work, the loss number, the first one from the epoch, like how it's 0.66, ideally we're wanting that number to get closer to 0.
Yeah, I believe so. Yeah.
So is it the reason why it's like getting further away because we keep like iterating through and then increasing that number? Is that kind of what's going on?
I don't think it's the number of iterations. And to be totally honest, I am not sure.
Okay.
Yeah. Um, my understanding is like with these machine models to like train a good model, like you might do it for thousands of epochs, but also a lot of this is essentially hand tuning. Um, and there's some general guidelines that I know a little bit, but not a lot that we've talked about you should have the layers gradually get smaller and stuff. But the truth is, I haven't done a lot of machine learning and AI, though I have worked with people who have, and they have told me that the fine tuning of the model is a bit of a dark art. Um, we'll talk about what the back propagation is doing in a minute, but it's essentially all these weights and biases are random, and then it kind of tries to tweak them to fit better based on the loss function. So it could be maybe I need to change the learning rate of my optimizer. And we'll talk about what that is in a second. It could be if we go all the way back up to the model, maybe for whatever reason with this data, I have too many linear layers. And a lot of this, even in the real world for people with a lot of experience, comes down to trial and error to figure out what will make the model perform better. Which I realize is a bit of hand waving, but the truth is there actually is a bit of hand waving in this, in that like these are not linear processes, and a lot of this really is hand tuning. And those big models like ChatGPT and stuff, they do a ton of hand tuning with stuff. Where we end up when we run a whole bunch of epochs, though, is we get, you know, a whole bunch of data points. And what that does is it lets our model do better each time. And I definitely have something not working right in my model, and I'm not sure if it's the model design. I suspect it is. But the more data points we have, the better this gets fleshed out. And I'll walk through it in full. But once we have once we have the loss curve, the optimizer's job is to figure out how to bring us closer to zero. But the optimizer, like, it could get stuck in here, right? Because if we start out over here with these weights and biases that are really bad, and the optimizer takes us over towards this, and it gets better and better and better and better. But maybe we have to like make some pretty big changes to the weights and biases. I can't just like increase them in a normal linear way, like adding 2 or whatever, to get it lower. Because if we look at this graph, we see that if I keep going in this direction, in fact, my loss gets worse. And I need part of the optimizer's job is to not get stuck in, they call them like local minimum or maximum, and to be able to kind of like jump over there. And we'll talk about that a bit more in a minute. I think it might be useful to take a quick look at the water potability code. And I actually am a bit curious about if we look at the code here in the dataset notebook to see how they did their model. And they do a whole bunch of stuff because they do a whole bunch of exploring of the data and predicting. They think about things we haven't even thought about, like if there's physically possible but extreme values, right? They've done a lot more data cleaning. They've done all this data analysis. So it could be maybe our data pre-processing wasn't good enough. Let's see if they finally train a model here. And we can see here where they're using a totally different algorithm that I'm actually not familiar with at all. Something called random forest. And I'm honestly not that sure what it does. It probably does more than the binary classification we did. We see here some very similar steps though. We're dropping our label to get our features. They're splitting the data into their training and test sets just like we did. Their test size is only 20%. It looks like they've added some randomness. I'm not exactly sure what that does. I'm honestly not sure what this does. They have a lot more complexity in how they've set up their model and what this is doing. This is going a bit beyond what we see here. If we kind of scroll through here, let's see if they do anything interesting. Um, this looks like more probability distribution stuff. And now it looks like they're fitting the model. I want to see if we can see like the training. So it looks like they got to like 76, 77. They got into like the 70s in terms of correctness and precision in training. Then for the final exam, though, they did worse. And they were in like between like 50 and 60% with how good they were. Um, and this kind of is a bit more of a breakdown on this. And so with all this work, they got an overall accuracy of 64%, right? And I think the takeaway from this is there's a lot of manual tuning and a lot of steps here to come up with a good model. And so I'm not that surprised that our water portability model that we built now, frankly, sucks, right? I will follow up a bit, I think, to come up with some better answers about what we can do to make it better. And to be honest, that's an area where I need to learn as well. But this is kind of the norm for like creating machine learning models. Like there's all these factors, and a whole lot of it is frankly trial and error, right? Like this person, even with all the extra stuff they added, I can guarantee they did a whole ton of fiddling with all of their values and stuff like that. Um, and then they're kind of talking about some of the problems they encountered and some potential issues and some other kind of interesting stuff. And I think that's probably a good stopping point there with that. Um, I'm curious if there's a binary classification. Here's a simple classification model. Let's see how this one does and how this one looks compared to ours. Again, they actually do a whole lot more data analysis than we do, right? So let's kind of skip through this and see if we can get to the good part. I'm not sure if there is a good part for this particular one. Let's see here. They do some training. Yeah, they're doing a more complex kind of training as well. So like we're very much dipping our toes in the water here. So again, I don't want to hand wave, but I think the genuine answer to why does our model suck right now is probably 50%. There might be some easy wins here, and 50%. A lot of this is fine. It just involves a lot of fine tuning. I'll poke around and see if I can find a good one that has like a nice binary classification of the water potability to share or build one because I think that would be good for us to see. Let's dig into this code though, because there's a couple things here that are really good to talk about. Um, Before I do, let me just check in and see what questions folks have and what's on people's minds. Because I wrote a bunch of code and we did some talking, but we didn't really walk through it. So what questions do folks have and what would you like to dig into more?
I have a quick question. Is this basically like in the curriculum for today? Is this kind of what we're going over to? And like the README and stuff?
Yeah, the
Okay.
curriculum we meet today, like we've pretty much come to the end of it. The one thing we haven't done that we'll do in a couple minutes is use our test data to evaluate the overall accuracy of our model. And that could be cool to see. Um, but so today it's very much going to be now that we've gone through this as a class, work with your pair programming partner to build one of these and play around with it, right? So let's talk a bit about what these things do, and let's go through it step by step. And let me go back down to, I think, our diagram here with the loss function and play around with it a bit. Because now we can really talk about outputs and loss functions and back propagation and stuff like that. So what happens when I run this code is for 5 times, we go through all of our data, and it's in batches, right? And we go ahead and we run the model on all the training data in the batch, and we give it the features. Then we figure out how wrong we were. And I don't want to get into the exact math. There's probably more, but the essence is the loss function takes the right answer, which is the label, right? Potability, and it just subtracts from it what our model outputted and gives us the difference. And it's, in essence, we can think of it as being similar to, I got 4 out of 10 questions right on the practice quiz. It's the difference between the prediction and the correct answer. Back propagation is where it gets a little more interesting. And as I've kind of talked about, the job of back propagation, which I believe happens here, is to figure out what parts of the model did bad. Did I struggle on the algebra questions or the vocabulary questions? If I'm walking from New Orleans to Seattle, did I make a right turn and, go to Texas? And so the back propagation algorithm, it uses something called gradient descent, I think, and I don't want to get into it too much, but it uses the loss function and it works its way back and it looks at the weights and biases for each and sees how much they contributed to the wrong answer. And it does this for each layer, and it goes all the way back, right? And so that's sort of the back propagation step. We're sort of like reversing the flow of data to figure out, like, where did I go wrong? Let me retrace my steps. And so back propagation is where did I go wrong? And maybe I went 500 miles too far east, right? If we're talking about, if I'm looking at a map and I'm trying to figure out where I'm supposed to go, and back propagation, it's kind of like having a compass direction. But, if I know that I need to go north, right? If I'm going from, I don't know, New Orleans to Texas, and like I end up over here, well, I need to go here, but just having a compass heading doesn't help me know how far I've got to go, right? Or I'm going from New Orleans to Seattle, excuse me. If we've got, let's just call this New Orleans, and let's just call this Seattle, right? Because I might know, okay, back propagation says I have to go northwest to get back on track. But how far? 5 feet, 10 feet, 100 miles, 10,000 miles? I need to chunk up my journey into steps. So I'm probably going to get lost again along the way, and and like need to come back here. And, you know, it's a journey of 1,000 miles. And so the optimizer's job how far do we go in the right direction? How much do we do? How many hours should I spend studying algebra and how many hours studying vocabulary? And that's what this learning, I want to say rate. Let me make sure I have the term right here. Yeah, that's what the learning rate is right here. And so we have a very small learning rate. And so the optimizer is saying, okay, go northwest, but just go like 2 miles at a time, right? Go in little steps. Because I might have a huge learning rate. And let's change this to 0.5, which I think would probably be ridiculously huge. And let's just run this with 200 epochs just for fun. And all of a sudden we have like massive loss functions, right? Because I've overshot Seattle and I hit like the North Pole because I moved in giant steps. So I really want my learning rate to be small. And maybe 0.2, right? Because the bigger the learning rate, the faster the change. And look how even that change from 0.01 to 0.02 kind of has a huge impact on the loss function. Because I think this was what, 0.01 just a minute ago. Yeah, we had 5 epochs and it was 0.01. But if we run this again for 200, you know, the model the other issue here is our model remembers between epochs. I don't think I've totally reset the model back to 0. I need to double check that, but I am relatively sure. Let me actually double check that. Yeah. So part of what we're seeing here is the model does maintain its values between epochs. Let's actually see how to reset the model. And honestly, AI is telling me that the easiest way to reset the model is just by making a new one. Right? So it's sort of like if I realize I have a bad design and I tweak the design, I might need to start from scratch and start over. But because we haven't done that, part of what we're seeing with this change in the loss function is we're running it more and more and more. So I'm surprised that this loss function this value has gotten so big, to be honest. But we've also like throwing in 0.5 was a pretty crazy value. So that's one important thing to think about here is our learning rate. And I do believe we want to keep it pretty small. With a higher rate, we overshoot. If it's too low, it might take too long. So this is something I think it would be interesting to play around with and see how it changes. And in fact, why don't we just reset the model once and let's do it right up here. And Let's have a learning rate of 0.2. And so now we see I've reset the model and our loss function is back to what we're used to seeing. It's still pretty wrong, to be honest. It got wrong faster. I see a lot more sevens here. I'm going to comment this out so I don't continually reset my model. And if we run more epochs with this slightly higher learning rate, I'm not sure I necessarily see an improvement. So playing with the learning rate is something that can be really interesting to mess with. There are different optimizing algorithms. The one here that we're using, Atom, is good because part of what it does is, if I go back to this diagram here, part of what Atom tries to do is avoid getting stuck in a local minimum. So it's a reasonable optimizer to choose. We've talked a bit about backpropagation and what's happening there conceptually. I don't want to go too much into the math of that, and to be honest, I would probably get a little lost in the sauce. So I think what I want to do to wrap up, especially as we're at time, is let's actually test our model. Now that we've trained it on the training data, let's use the testing and evaluation data to see how well the model performs overall. And we've done a lot of epochs here, right? Because I've been hitting repeat on this. And so we've probably done, I don't know, 1,000 epochs. So let's see how we do, right? Because I've kind of just been guessing at the overall performance from eyeballing these loss numbers, but let's actually write some code and see what that looks like. And we're going to import a library from Torch. And I actually may need to install Torch metrics as a Python dependency. And it looks like it's already there. I think I may have a typo. That actually seems to be working now. I think VS Code may have just been taking its time and gotten a little confused. And as it sounds like this accuracy class is going to help us figure out how accurate our model is overall. And we are going to tell it that it's working with a binary classification model. And I do need to fix that line there. So we're importing class. If we do a quick hover, we can see if we have any useful information. And it's going to do a bunch of math. And it kind of gets into the math of this, and we don't need to look at this too much, but I think it's always good to just glance at this and see what it is. We could look at the PyTorch website for more. We need to set the model to evaluation mode now that we're done training. And now we do need to make a loop, and we're going to let PyTorch tell us when we're done. It's going to use some math called, I think, a gradient descent to keep running the evaluation. And we're going to loop through our testing data. And we are going to run the model in evaluation mode with our testing data. And we're going to get what the predicted output should be by our model. And then we're going to compare it and have the accuracy class keep track of how we do for each run with the actual answer. And then when we're done, and I'm going to fix the typo I have here, finally, we're going to print out our accuracy score. And we're going to use the accuracy class to compute it. And this is going to spit out a whole bunch of stuff, so we need to call this item method to get a nice looking number. And now if we run this, that's actually not terrible. 62.5% accuracy. If we go up here and we throw a couple more epochs in, so we're running 200 epochs there. And let's just throw another 200 in for fun. So we've now done 400 more epochs, which again, just as a reminder, is 400 times through the whole data set that we've batched up. Let's see what our accuracy looks like now, and if it's improved from 62.5 or not. And it looks like it's still exactly the same. Unless I've done something wrong, or maybe the testing data is more limited. But I'm also not entirely surprised. Like, if our model isn't very good, then it makes sense that we don't see big changes in the accuracy number. So that's really the last thing to cover. We've covered a whole lot of ground. Right? We've covered reviewing and building our model. If we go all the way back up here, we imported everything we need. We made our binary model class with all of our input layers and hidden layers and our sigmoid. And now that we're actually doing learning, it would be really interesting to tweak this. We'll talk more tomorrow, I believe, about optimization. But we've done our data pre-processing to do the key steps of getting rid of nulls, putting everything in pandas, normalizing the data, features and targets, and getting test data and training data. We've stuck it into data loaders so that PyTorch can do all these learning runs for us, and the learning model can do its thing. And then we actually ran the training loop. And I skipped over that over here, where we actually run our model against all the data thousands of times. And we do backpropagation to see how wrong we were and where we went wrong with the loss function and backpropagation. And then optimization tries to tell us how many steps we should take to get closer to a good prediction. And we saw that it's not easy, that our model performs pretty poorly. And then finally, we saw how to actually test the model for accuracy. Because as you all can see, doing this is way better than just eyeballing, thousands of loss function outputs. So this is really the way to look at the accuracy of our model. I know we covered a lot of ground and we're a little past time. So why don't we break for lunch? Because I don't want to keep people, and we do have a Beyond Tech Talk at 1:30 Central, where I'll be talking about imposter syndrome. But I'm happy to stick around a bit to answer questions folks that people may have. So let me open up the breakout rooms for people who want to use them. And give me one sec here. And have a good lunch, folks. And I'll send out pairs for after the Beyond Tech Talk, and the task really will be to do what we did today together and play around with it. And I think that's a pretty solid task right there. And tomorrow we will be talking a bit more about optimization. Now that we've trained this model, how can we actually make it better? So thank you very much. And what questions do folks have and what's on people's minds? And let me go ahead and stop the recording.